My intro, you touched on a lot of things that I'm going to be talking about today, so thanks. So, as Michael said, I'm Saleema Amershi. I'm a researcher at Microsoft Research in the CHILL group, which stands for Computer-Human Interactive Learning. And I'm going to talk to you today about some of the work that our group is doing in collaboration with also a number of other folks at MSR and some fabulous interns that we've had on how we can work towards more usable machine learning. And feel free to throw out the talk if you have questions. Just raise your hand and let me know. So first of all, why do we care about machine learning? So we care about machine learning because we have all of this data, right? We have all this data that's being collected about us from our interactions, on the web, or interactions with our computers, and from all our sensory-equipped devices. And machine learning is this really powerful way of sort of transforming the raw data that we have out there into usable information. And so what I mean by usable information, I mean sort of a machine-learned model that can be used to make predictions. And these models are what we can deploy in our applications in order to automate our tasks, right? So we can use them to sort of automatically detect objects or patterns in data. We can use them to sort of automatically try to organize and manage our information, as well as sort of predict future behaviors. And so the way that this works, at least with supervised machine learning, is something like this, where given some labeled data, where the X's here are the data and the Y's are the labels on the data, the goal is to learn some function that can predict the labels on new data. So that's the overall idea of supervised machine learning. But now in practice, what really happens is there's this guy, right? There's a guy who's responsible for collecting some data, creating some features, and this is the guy. He's responsible for getting the data together, creating features, tweaking algorithm parameters, and then sending all this information to a machine learning algorithm in order to try to learn this function. And this is, typically an iterative process in that this guy's not going to get it right the first time, right? He often has to look at how well the machine is performing and, try to inspect what's happening and then try to improve the model by continually trying to supply it with more and more information until it's working the way he wants it to. Then the output of this process is a model that's really encapsulating this learned function. And this model, like I said, can be deployed then in your applications, and then your applications can now, take in new data and can use this model to make predictions. So, for example, machine learned models are being used, in everything from sort of recommending interesting content to you on the web, so music recommendations or, Facebook or Twitter posts, to predicting, the relevance of ads for you, even to, like detecting fraud or, detecting even the outbreak of diseases. The problem is that, while machine learning is being used for a lot of these really important tasks, the models that people create are not always accurate. And that's because, models are really a function of both a complicated algorithm and complex data, which means that, sometimes they can pick up on sort of patterns that aren't really there, and those can lead to sort of bad predictions. And so the consequences of these sort of inaccurate models can range from being benign, where you might get some unwanted Twitter or Facebook posts or irrelevant content recommendations, to really damaging, where financial or political decisions are being made based on inaccurate predictions, or worse yet, are made based on predictions that might encode some inherent biases in the models. And so, machine learning people are working on this, right? They're working on trying to improve machine learning algorithms so that they can make better predictions or make them more efficiently. And we need that. But, we have to remember that there's, also this guy, right? This guy is, the one who's like providing the algorithm with information and iteratively trying to debug the performance of the models that are being built. And so, the ability of this guy to effectively train these algorithms really directly impacts the performance of the models that are being built. And the problem is not that this guy doesn't have the right skills, although that can also be a problem. But even machine learning experts, have difficulty building models or understanding exactly how their models that they build are going to perform in the wild and on totally new data. And in fact, these human limitations are something that machine learning researchers are aware of. They try to design algorithms to account for some of these human limitations themselves, right? So, for example, there's a lot of work being done on designing algorithms that can work in the face of like noisy data or insufficient data that might come from a human. But there's also sort of another strategy. There's a complementary strategy, which is instead of trying to deal with human limitations in the algorithms, we can actually try to improve human abilities by trying to design new tools and interfaces in order to try to reduce or prevent noisy human input altogether. And this is what I'm going to talk about today. I'm going to give you a couple of examples of some of the work that our group is doing in this space, where we're trying to sort of shift some of our attention over to the user and try to design new ways for this guy or people to better interact with machine learning systems. So I'm going to give you a couple of examples of this. Like I said, so I'm going to talk first of all about something to do with the input side, which is what we call structured labeling. So it has to do with how people provide labeled data to machine learning systems. And then I'll talk in the second half of the talk about the output side, and so how we can sort of design better tools for people to understand the performance of their models. And then at the end, I'll talk about some of the other work that our group is doing in this space and some of the open opportunities there. OK, so structured labeling. So this was a project we did a couple years ago with an intern of mine from Oregon State, Todd Kalisa, as well as several other folks at MSR. And just to give you a little bit of context, recall that supervised machine learning systems learn from labeled data. Now, oftentimes, people are actually recruited to manually label large data sets for the purpose of training these algorithms, which seems simple enough. But the problem is that labeling data is actually not really as easy as it seems. And this is something that Michael talked about, right? When people label data, they're labeling according to some target concept that's in their heads, right? So for example, imagine I was asked to label web pages as being about cooking or not related to cooking. So what I would do is I would start labeling some examples that are clearly about cooking. So this is a recipe page, so it clearly has something to do with cooking. Here's another example. Then I would label some pages that are clearly not about cooking. So these have nothing to do with sort of cooking. Then I might come across a page that looks like this, right? So this is a page, it's a catering page, which is kind of like cooking. It's about sort of preparing food. So I might say at this point that yes, this is about cooking. Then, I'd keep going, labeling more and more examples, more positive examples and more negative examples. And then I might come across a page that looks like this, right? So this page is, kind of like that catering page in that, it's about someone coming to your house and preparing food for you. But, at this point, if I think about it, maybe I would say that, this is really not about cooking. It's about someone else cooking for you. It's not really about the process of cooking. So maybe at this point, I'll say that, this is actually not about cooking. Okay, so that's the problem, right? The problem is that I just inconsistently labeled my data, right? I labeled this page as not about cooking, but that previous page as about cooking. And did I even remember that I did that? And are there more pages like that? You can imagine if you have hundreds or thousands of data points, will you remember that how you labeled previous examples? Do you need to go back and find them and move them now that you've changed your mind about what you want to consider as part of your concept? So the problem is that the concept that people are labeling for is evolving as they observe data. And so to understand sort of how much of a problem this actually was, we did a study where we had 9 machine learning experts label the same set of data over 2 sessions, about 4 weeks apart. And what we found was that even machine learning experts were only about 80% consistent with themselves on labeling the exact same set of data. And in fact, 6 out of the 9 people's labels changed significantly from one session to the next. Okay, so this concept evolution, it happens. It's something that happens to the user. It's something that's happening in their heads as they label data. But the tools that we have don't allow us to sort of easily revise and refine our concepts as we go along. And this can sort of be both frustrating to the user if they want to change their minds, but also can be harmful to some machine learning algorithms that fundamentally assume similar items have similar labels. Yes? One question about that. Yeah.
Is that evidence of evolution, which would be sort of like a changing bias, or is that just evidence of sort of randomness in my labeling?
Yeah, there's some randomness that happens, but there's also changes, and we sort of see this in the study that I'll talk about, because we see that people do want to change their mind and they do move things around. And even when you work with machine learning folks or people who are labeling data, they often will use our system and then come to us and say like, well, I changed my mind and I want to make all of those examples that I labeled for this subconcept in a different way. And really the only way that they can do that is to go through every example, find those, or search for them somehow and move it. So it's a bit of both. And I'll talk a little bit more about this at the end, because like some algorithms can handle some noise. And it actually can be good for some machine learning algorithms, whereas some algorithms are more affected by noise. So you know, there's differences there. But having people sort of understand how they label can lower their frustration, can lower a lot of their anxiety, which we also sort of found in the study. And so I'll actually show you with the tool we came up with to sort of help people with this process. It's actually a technique that we call structured labeling, where we essentially allowed people to sort of explicitly organize their concept using sort of grouping and tagging within a traditional labeling scheme. So what I mean by that is that instead of something like this, where you sort of force people to categorize data at a high level, we had something like this, where we allowed people to create subgroups within these high-level categories. So for example, if I had, came across this catering page, and if I was unsure about it, what I could do is create a subgroup for it within the cooking category. And then I can tag that subgroup, maybe with something like catering, so that I could sort of remember how I labeled examples of this kind. Which means that, what that does is that it's surfacing my labeling decisions to myself, so that later on, when I come across like other catering examples, I can say that, well, this is actually very related to that other catering page that I saw, so I can group them together. And then later on, if I decide that maybe catering should not be part of my concept, I can easily revise my concept by moving the whole group at once. So these groups and tags sort of, not only allow me to recall and revise my labeling decisions as we go along, it actually lets people sort of defer their decision making. So this is what I was sort of referring to. So people often sort of agonize about like how they should label data. If I came across that catering page, I might, should this be positive? Should this be negative? I don't know. And oftentimes people get, very afraid of like what their labels are going to do. And so what this does is sort of allows people to defer their decision making, right? So they can tag things that they might not be sure about, and they can always go back and revise them later if they change their mind as they observe more and more data. So we also came up with an assisted version of the structured labeling tool to sort of deal with a few problems that we saw during a pilot study with the tool. So first of all, what we noticed was that oftentimes actually, people didn't provide tags for the groups that they created. So they would sort of create these subgroups quickly, put things aside that they weren't sure about, but they didn't want to put in the effort to sort of write tags for them. But then later on, when they, recall that they created a group of something, before, they'd have to actually like look into the groups in order to see what they had put into all of them. And that was a big pain. So to help people with that, we provided automatic summaries for the people of the groups that they created. So this is just using the text in the groups that people created just to help them sort of recall what each group was in case they didn't manually tag it. But we still allowed them to do that as well. We also found that when people were labeling, they would often remember creating groups with similar items to the one that they were currently trying to label. But they would forget sort of exactly which group they had put those similar items in. And so what we did was we provided recommendations based on the similarity between the current item a person was trying to label and the groups that they already created. So this with this little star here, and so that would sort of the system is sort of suggesting, well, you put something similar like this in this group, so that might help them sort of decide how to group things. Another interesting thing that we saw was that people didn't want to sort of put in the effort to make these labeling decisions for items that they thought were sort of outliers. So if there's only sort of one catering example in all of my data, then it doesn't really matter whether I consider it positive or negative. But if that example is sort of representative of a larger subconcept that I really want my model to recognize, then I might want to put in more effort to label it. And so to deal with this, what we did was we showed people similar examples to the example that they were currently trying to label. So we would show sort of the things that the system thought were similar, just to give them a sense of like how sort of big this group is and whether or not they should sort of bother trying to structure their labels for. Okay, so we did an evaluation to understand, to try to understand sort of the impacts that structured labeling had on the labeling task. Where we had 15 participants come in. We had the within subjects design, so we had them use each of these different conditions, the traditional labeling tool, as well as the manual and assisted structured labeling tools. We had them label 100 pages, and we had them label for a few different concepts that we thought people would sort of be relatively familiar with. And what we found was that participants did indeed use structured labeling when it was available. We found that people created significantly more groups in both the structured labeling conditions than compared to the traditional labeling, where they couldn't do that. But interestingly, we noticed that people tended to create fewer but larger groups with the assisted condition. And that's probably because the system was making recommendations about where these subgroups were, or how they should create these subgroups based on their previous labeling decisions. We also found that people revised and revisited their labels significantly more with the structured labeling tools than with the traditional tools. So this sort of gets back to the idea like, is it noise, or are people sort of really trying to change their minds or wanting to sort of understand their labeling decisions? So people were looking back and they were trying to change things as when they had a tool that allowed them to do so. So we also looked at like the consistency of people's labels and found that with both structured labeling tools, people labeled significantly more consistently than with the traditional labeling tool, with no real significant difference between the manual and the assisted conditions. So this is great. This is what we wanted, but the consistency and the ability to evolve your concept did come at a cost. Right? It actually took people longer to complete the labeling task with the structured labeling conditions, which makes sense because people are putting, they have to do more work. They have to create these subgroups and decide how to tag them and which groups to create. But interestingly, when we looked at sort of the difference in how long it took people to label in the first half of the study versus the second half, we saw that this difference in speed really decreased. And this was likely due to people sort of converging after a while on what they wanted the definition of their concept to be. So there's some upfront cost to having the structure, but it decreases over time. We also found that people preferred the structured labeling condition for most tasks, saying that it helped them to sort of organize the items that they wanted to label. Interestingly, in terms of the assisted condition, some people said that they preferred it because it actually sort of converted a decision-making task into sort of a verification one, right? So with the recommendations, the user can say like, well, actually I want it to be somewhere else, instead of having to decide how they want to label. And of course, some people did say that they preferred the traditional tool because it was simple. But a lot of those people wanted the structured labeling tool in certain cases where they were sort of less familiar with their concept, right? So if you know exactly what you want to include as positive or negative examples, then maybe you don't need a structured labeling tool. But if you're sort of more fuzzy on the concept, then having something like this they thought would be helpful. Okay, so. To summarize, people evolve their concepts as they observe data, but the current tools that people have, don't allow them to sort of revise and recall their decision making. And so we proposed this technique called structured labeling to help them, and found that people did use it, and it helped help them label more consistently. And so sort of going back to the consistency issue, like I said, some algorithms are more affected by labeling inconsistency than others, particularly like highly expressive algorithms can try to overfit to the noise in the data, and so they may be more affected than less expressive ones. But even regardless, this is something that's happening to the user, right? So it's causing frustration to the user if they want to change their mind about how they want their algorithms to behave. So it's something that's still happening that can still benefit the labelers themselves. And the structure also itself contains information, right? It contains information that you can use in order to come up with features, for example, that can sort of help your algorithm learn about sort of these sub-concepts. It contains information, we can sort of measure the performance of your model on each of the different subclusters, which can help you sort of make decisions about what you want to include or not. So there's a lot of actual information that's contained within these groups and tags that we can also use in order to try to improve the performance of the models that we build. Okay, so are there questions about structured labeling? So this is just sort of one way that we're trying to help people better interact with machine learning systems. I'm going to talk about sort of the output side after that. If there are no questions right now, we could also have questions at the end. Okay, I'll keep going. Model tracker has to do with the output side of this process, which is sort of, what people are, for building models, they need to sort of understand the performance of the models in order to try to iterate. And so, what happens in this process is that when you're building a model, the output that you see in every iteration should directly influence your subsequent actions. Right? That's really the idea of seeing sort of performance results. If your model is performing poorly, then you're going to try to go in and fix it. The problem is that most of the time what we see at this stage is something like this, right? Some number that summarizes the overall performance of your model. The problem is that, what does that really tell you, right? It can signal that there is a problem, but it doesn't really tell you anything about, where those problems are or how you should deal with them or what you should deal with first. And even if you're lucky and if you have several summary statistics or the sort of standard confusion matrices or precision recall curves, sort of the standard techniques that people use to understand the performance of their models, all of these techniques convey the existence of errors, but they don't tell you where those errors are or what you should do about them. And for that, what you usually have to do is actually switch to a different tool or a different mode to actually pull up your data or visualize your errors. And these types of tools are often heavyweight, meaning that you often have to sort of convert your data into different form and then use a different tool to visualize. And even if you have a tool that can do that, once you've loaded up your data, you still have to sort of sort and filter in order to find errors and then try to gain insights about what the problems might be. So the problem is that this, switching between these summary statistics to heavyweight tools for debugging can actually be very disruptive to your primary task, which is to build a model. And in fact, this problem has been shown to lead to a trial and error approach to model building, meaning that people, instead of looking at their data at every iteration to try to see what's happening, they will randomly try to change parameters of their model, tweak parameters, or add features in order to try to make these summary statistics go up, right? And then only when that fails, then will they actually sort of resort to looking at their data and trying to sort of understand what's really going on. So the model tracker project was really, us trying to figure out how we could sort of encourage people or enable people to take a more informed approach to model building. So I will attempt to demo the tool. So let me switch this. Aha, okay, cool. Okay, so I go back. So it's a little bit slow. Okay, so this is this whole system is called ICE, Interactive Classification and Extraction, and this is a platform that our group at MSR is building to enable non-experts to build classifiers and entity extractors over big data in one sitting, in a few hours. And so, I won't be able to talk a lot about it today, but, for the purposes of this talk, you just need to know that up here is where you would label data. So I could say these are positive or negative and submit data to my model. And over on the left is where a person can sort of provide features for their model to learn with. Now, in this case, I've already built a model using ICE. So I've tried to train a classifier to recognize whether web pages are about cycling or not cycling. So in this case, I've already labeled about 511 items and provided 6 features. Now, in ICE, what we used to have is what you see here below. These are the sort of standard summary statistics and graphs that you might use when you're trying to use machine learning. So people sort of would interact with their system, label data, create features, and then look at these summary statistics in order to try to see what's going on. And then when they thought that there was a problem, they would switch over to a review mode where they could do things like sort and filter. So they could filter by errors. And it's a little bit slow, but they'll pull up sort of the data that you've already labeled that's in error, and then you can sort of page through those items in order to try to sort of gain some insights and understand what's going on. This should be pulling up data, but it's a little slow, but you get the idea. So what we did in this project was replace all of these standard summary statistics and graphs with this single visualization, which you see here below, which we call model tracker. So I'll explain what it's showing. So each of these little boxes corresponds to an example that I've already labeled. So in this case, I've labeled 511 examples. So there's 511 boxes. The color of the box is the label that I gave. So if I said something was positive, it's going to be green. If I said something is negative, it's going to be red. Now, the boxes are laid out horizontally according to my classifier score, with low-scoring examples to the left and high-scoring examples to the right. So what that means is what I want this visualization to look like is I want all my green boxes to be on the right and all my red boxes to be on the left, right? Because that would mean that my system is very much agreeing with what I told it to. Similarly, errors are also visible in this way, because errors are the red boxes that are to the right, so red boxes that are getting high scores, and green boxes that are shown to the left. So what this is doing is it's showing me performance, right? It's showing me where my errors are. But unlike with summary statistics that sort of treat all errors equally, this is actually showing me not only my errors, but it's showing me sort of the severity of my errors, where more severe sort of errors, more egregious errors are sort of the ones that are at the far ends of the visualization, because that's where the system and I very much disagree. As opposed to sort of this uncertain middle area where the system is sort of more confused. So what that does is it allows people to sort of prioritize their efforts in debugging. And in addition, because we're showing data at the item level, you can actually click on these, right? You can actually click on them to pull up the errors directly. So it's providing you direct access to your data. So you don't have to go search for problems and then try to sort of gain some insights from them and figure out what's going on. So for in this case, I clicked on this this green box, which is at the far left corner. So something I labeled as positive, but the system's giving a really low score. And this page, so I was trying to create a classifier that can recognize whether a page is about cycling or not. This is actually a recycling page, so that I actually labeled as positive. So that's actually a mislabel on my part, and that actually happens quite often. So what I can do is directly change it. So I can change my label, update my model, and then the system will retrain, possibly, and it would update this visualization once it retrained. So again, you'll have to imagine, but it would fix the error, and then the visualization would update into something's not or something's failing, but that's the idea. The idea is you can directly access the errors and sort of look at them and then try to sort of fix them as you go along. Yes?
Oh, and what's the other page that was shown? Is that a true negative example?
Yeah, so if you notice, so when I click on these boxes, do you see these lines that are showing up connecting the item that I clicked on to other examples? It's actually showing me, and it will pull up the other examples that I'm connected to. So it's showing me examples that the system thinks is very similar in my current feature space. And the idea behind that was that if there are examples that you label differently, but the system sees as very much the same in the feature space, that likely means that there's a feature problem. You're seeing something that the system is not seeing because it thinks these two are very different. So in that case, that can give you information about how to debug, and then you can add a feature in order to try to fix your error. And I would show that now, but I'm afraid it won't update. So maybe I can show a little video at the end, just to give you a sense of what the update looks like. So that's what model tracker shows. But so I want to explain that also Model Tracker actually subsumes the same information that we see in all of these summary statistics and graphs. So I want to explain that. So first of all, confusion matrices. So are people familiar with confusion matrices? Okay, so confusion matrices, are just showing you the agreements and disagreements between your labels and the system's predictions. Right, so things that I labeled as positive, in this case, there's 34 examples that I labeled as positive that the system also thinks is positive, but there are 7 examples that are in error, 7 examples that I said was positive and the system said was negative. So showing you agreements and disagreements. Model Tracker, you also see agreements and disagreements. You're seeing, errors. Disagreements are red boxes to the right and green boxes to the left, and agreements are green boxes to the right and red boxes to the left. But now, unlike with confusion matrices, which are threshold dependent, Model Tracker is actually threshold independent. So what do I mean? So to create a confusion matrix, you have to set a threshold, right? So if I wanted to sort of see the performance of my model at a different threshold, I would actually have to change the threshold so that we have a slider here that allows us to do that. And then you would be able to generate a new confusion matrix to see sort of what the performance is at that threshold. With Model Tracker, you can see the performance at all thresholds at once. So you can see that, so we have a threshold line here, but actually it doesn't serve any functional purpose. It serves as a visual aid. And so what it can do is like if I move my threshold to the right, I can see that, I'm reducing the number of false positives because I have fewer red boxes to the right, but it's coming at a cost of false negatives because now I have more green boxes that are to the left. So you can sort of see the trade-off between your false positives and false negatives, your agreements and disagreements at all thresholds at once. So if you wanted to see the sort of same information with confusion matrices, you would need one of these for each threshold that you're interested in, which can be up to like 100. Model Tracker also shows you the same information that you would see in precision recall curves. Are people familiar with precision recall curves? Yeah. Okay. Some. So precision, is it's the number of true positives over the number of true positives and false positives, and recall is sort of the true positives over true positives and false negatives, something like that. And if that's confusing, don't worry because it's confusing for everybody. Like it's even machine learning experts. I often see sort of trying to do this mental mapping in their head, like so precision is this over this, and what does that actually translate to? With Model Tracker, you can actually see this directly. So precision in Model Tracker are the number of green boxes that are to the right of this threshold line, right? So in this case, I'm doing pretty well in terms of precision because most of what you see on the right is positive. But recall is the number of green boxes that are to the right. And so there's a lot of green boxes that the system is predicting as negative. So I'm actually doing pretty bad in terms of recall. And so you can actually see the precision and recall trade-off at the various thresholds as well, because if I were to move my threshold line to the left, I'd be increasing recall because more green boxes are being predicted as positive, but it's clearly coming at a cost of precision because now also more I'm predicting more red boxes as positive. So you can see all of that as well. So you can see sort of what these standard precision recall curves will show you. So subsuming all of the information that we would normally see, but also providing you direct access to your errors so that we can sort of encourage people to look at their data and understand what's going on with every iteration. We also do a whole bunch of other things, like because you're showing data at the item level, you can do a lot of annotations to this. So you might notice some of these annotations I have here. So I've sort of tagged items that I want to sort of keep track of, and so as I'm going along, if I try to fix those errors, I might want to tag it to see if it actually got fixed as a result of my action. So I can do that. You see these little circles here. Those are showing me sort of outliers that what the system thinks are outliers. So that can sort of give me additional debugging information. If I look at one of those, I might see that maybe it's showing me something that it's only seen one example of this kind, so I might need to provide more examples. We can also show feature information. So if I hover over these features, I can sort of see how that feature is correlated with my class. So that can sort of help me sort of debug at the feature level. So there's a lot of things we can do because we're showing data at the item level. OK, so that's Model Tracker. Maybe I'll try to show you a quick video. I'll forward to like the end of this. I just wanted you to see sort of how it would normally look like. So I clicked on an example, changing the label, adding a feature in order to fix a problem that I've seen. And the system is going to actually like take that information now and update. And it can show you, you can sort of track your progress as you go along. And when you use Model Tracker, if your model is performing, if it's learning as you go, you'll sort of see these classes sort of separate. You'd see like green boxes moving to the right and red boxes to the left. And if you saw those directed arcs, that's showing you sort of the impact of your actions. So oftentimes, you'll see that with labeling, you don't see a lot of those arcs, you don't see big changes, but with featuring, you see a lot more. And so that can sort of help you decide whether or not the effect you thought was going to happen actually did happen. Yes?
You might have time. Could you show the entity extraction?
Sorry?
Would you have time to show the entity extraction?
I possibly. I don't even know if it will come up. Yeah, so yeah, we do use Model Tracker for entity extraction. Let me see if I can, let me change my session. Oh, okay, let me go back. Oh, no, it's fine. So I don't know if I have an entity extractor available. Okay, maybe I'll try to see if it loads after a while. But yeah, so we do use it for entity extraction. Entity extraction can be sort of seen as sort of a hierarchical multi-class kind of problem. So we actually use it for that. So it can be used. So Model Tracker can be used for multi-class in that way, where we sort of convert a multi-class problem to a binary problem, where for every class it's either that class or all or the rest. And so you have to sort of switch between different model trackers. But it's not necessarily the best way to do it. And we're sort of looking at how we can sort of provide a single visualization for multi-class, but we do use it that way currently, and people will use it, and they seem to like it. Okay, so I can skip all these backup slides since the demo sort of worked. Okay. So, Model Tracker deals with this problem that, current tools for performance analysis and debugging, are either too coarse to provide insights or disruptive to the primary task because you have to switch between them. And so we did a couple evaluations in trying to understand how people actually would use Model Tracker. Specifically, we wanted to see how people naturally use Model Tracker when they were building models. And how often they interacted with it. And then we also ran a sort of controlled experiment trying to understand that when people are interacting with the Model Tracker, are they able to debug their model's performance in the same way as they would if they were just sort of sorting and filtering through their data. So first, in terms of how people actually use Model Tracker, we actually did a 6-month deployment where we had 7 real users. So by real users, I mean people who are like not part of our team. And we had them, I mean, we're real people too, but people who are not part of our team. And we had them build real models, meaning models that they were actually building for research and product deployments. And what we found was that people did, in fact, use Model Tracker. They used it in 35 of the 40 sessions. And when they did use it, they used it throughout the model building process. So what this graph is showing you is how often people interacted with Model Tracker over time. And you can see that people used it throughout. They were clicking on items, boxes throughout the process with a slight increase in interaction towards the end. Yes?
Clarification. When they're not using Model Tracker, what are they doing?
So in ICE, you start from scratch when you're building a model. So you have to both find new examples in a universe, so in a large data set of, we have 50 million web pages. So they're searching and exploring the universe to find new data to give, as well as creating features. So Model Tracker is used for debugging each iteration of that model. So if you find a new pocket of example or a new island, then you would incorporate that into your model, and then you might look at Model Tracker to sort of see whether it got that or not. So yeah, they're doing the whole iterative model building process with ICE.
So is your ideal that this number should go up or down?
Over time?
In general.
I think I would say I would want people to have a sort of steady interaction with it over time, right? We wouldn't want them to just collect all of their data and build all these features and then debug at the very end, because as you're going along, you might see some problems which might change the way change things earlier on. It might lead you in a different direction, and you might change the features that you have, which you might not have seen if you weren't looking at your data as you go along. So a steady sort of interaction is what we really wanted.
I was asking maybe a little bit more about the average case. Like, if you wanted a higher number, then that would mean people are spending more time working with your system, developing their models, and so on.
Yeah.
And that seems good. But on the other hand, you also might want a lower number, because that means that they're being more effective about it and needing to spend less time refining their models.
Interesting.
I'm just trying to figure out, like, what's the target?
The target, yeah. Yeah, that's a good question. I think all machine learning requires iteration, and yeah, I think people can be more effective if they look at their data earlier. So yeah, if we're providing like the best means for them to like improve at every iteration, then maybe they only need to interact with it periodically. But it's really hard to say, because like current tools like that people use, they don't interact with their data very often. And we know it's a problem, right? We know that people are sort of taking this trial and error approach. So it's hard to say if that they're not looking at their data because they're doing better. Actually, it's more that it's just they're unable to do so. So it might be something that we'd be able to sort of see over time with more usage, to see what the effects are. No.
It might be interesting to sort of take the average of this and try to correlate it with like the final model performance.
Yeah. Definitely, yeah. So another thing we looked at is, we wanted to sort of see what people were actually clicking on in their data, and what we saw was that people did tend to click. So this is showing you sort of the prediction scores. So the things at the far ends are sort of correspond to the far ends of the visualization. So people are sort of interacting more with the data at the far ends, but they're still sort of clicking on things in the middle. And we actually talked to people, and they said that was actually a strategy that they naturally sort of took, because they felt like the problems at the very far ends had sort of more obvious solutions. They felt, there are things like mislabeled data, and so there were sort of the easier things that they wanted to sort of get rid of first, as opposed to sort of the items in the middle area, which they thought were sort of harder to deal with. So they sort of took this strategy. Interestingly, we also found that people, of the items that people clicked on, only 40% of them were actually in error at the time that they were clicked. And that was surprising to us. We thought that they would just sort of look at their errors. But in fact, people sort of wanted to look at other things as well, right? So first of all, they wanted to sometimes check what the system was getting correct, just to get a sense of like where it's working well. But also, this goes back to sort of what I said earlier, which is that, in typical, summary statistics and graphs, errors are sort of threshold dependent, right? So with Model Tracker, they're not, and you can click on anything. And so you might click on an example that, is technically correct, but it's just, below the threshold or just above the threshold. So it's still sort of problematic. So people are also wanting to click on that and sort of inspect those examples, even though they might technically not be in error. Okay, so we also did a controlled experiment comparing Model Tracker's support for debugging to sort of the traditional method of looking at your data via sort of sorting and filtering through lists. So we had 14 people come in. We had them fix a broken model using both Model Tracker and the traditional sorting and filtering. And what we found was that our participants preferred Model Tracker over those traditional tools without a loss in their ability to debug and actually find errors and understand what was going on. And that's sort of what we want. We want people to look at their data more frequently, and when they look at it, we still want them to be able to figure out what's going on and understand problems. And so, people sort of commented on their experiences and said things that, they thought the interface, the Model Tracker interface was, more intuitive. They thought it made, sort of these summary statistics and graphs more accessible. They liked the fact that, it was a single visualization. It was one thing they had to sort of keep track of, as opposed to sort of trying to interpret multiple summary statistics and graphs. And they also commented on the problem that they felt with the traditional tool, which is switching between these two different views in order to figure out what's happening. And of course, a couple of people did say that, they were used to this traditional summary statistics and graphs, and they felt like that, if they already knew what they meant, that maybe it would be okay. But a lot of them also said that they wanted some combination of the two and still having the ability to see the overall summary statistics, but having model tracker to access their data. Okay, so to summarize, we built Model Tracker to help people during this performance analysis stage during model building. And I showed you how Model Tracker actually sort of subsumes information contained in numerous summary statistics and graphs while providing direct access to your data. And we found that people naturally use Model Tracker throughout model building and preferred it over these traditional tools without a loss in their debugging ability. Okay, so I talked about how just like we have people working on trying to improve machine learning algorithms, we also have a really important opportunity, I believe, to improve the tools and techniques that people use, the people who are involved in the machine learning process. We have the opportunity to improve those systems, and I gave two examples of this today, looking at sort of both the input side and the output side of this problem. But there's a lot of opportunities remaining in the space. On the input side, there's helping people come up with features. I think still it's hard for people to think of new features. So there's opportunities there. It's hard for people to explore large data sets and find data to include in their models. It's hard for people to figure out which parameters, how to set the parameters for the various algorithms they might try to use. And on the output side, there's a lot of opportunities there as well, right? Like I showed you Model Tracker, which is really designed for binary, even though we use it for multi-class problems. But I think there's more we can do there. There's opportunities also to work with different types of algorithms that, if you can sort of visualize the flow of data through different algorithms, I think would be sort of really interesting and really helpful for people interacting with machine learning. And I think this is where HCI can really help. I think it's we're trained to sort of understand tasks and understand whether the tools that people use are actually helping them accomplish those tasks. So I think HCI can help with identifying where these problems are, because that's hard for people not in HCI because they're so used to using these tools that they've been using for a long time. So having a fresh perspective to understand whether the tools they're using are actually effective. And then HCI can also sort of help with coming up with new solutions to those problems, right? So designing new ways for people to interact. I think there are sort of a lot of opportunities for HCI to help with machine learning. And I really only sort of focused on the interface side of this problem, how the user can better interact with these systems. But I think advances in interfaces really go hand in hand with advances in algorithms, because the insights that we gain with understanding users can impact the algorithms we create, and vice versa. So I think there are a lot of opportunities for collaboration across HCI and machine learning and visualization as well. Okay, so this is what our group does at MSR, the CHILL group, Computer-Human Interactive Learning. We're building all of these things that I talked about and others into our ICE system that I mentioned earlier, which we're moving to the web soon. So soon, hopefully, you'll be able to use it if you want to, if you're doing work where you need to sort of build a model and want to deploy it and see, enable some application, you can do that as well. So if you're interested, contact me. We're also, we're always looking for great interns, if you're interested in this space. So feel free to talk to me about that after as well. So thanks. I can take questions now.
Thanks.
Yeah.
I'm wondering if I could dig into the visualization a little bit.
Yeah.
It's I feel like through hard-won experience, you start to learn that small differences in classifier confidence are not necessarily interpretable, nor should you pay tons of attention to them. Clearly there's strong positive, strong negative. But I wanted to sort of pick your brain a little bit about why you chose this continuous layout that sort of accentuates the fact that this is very close to this, but slightly more confident than this one.
Yeah.
Where those differences may or may not actually be something that would be productive to focus on.
Right.
They may be within noise, so to speak.
Yeah, and I don't think people sort of look at it in that way. They don't. I think globally they they compare, they see that there's these problems at the far ends, but between things that are sort of near each other, we don't see sort of a lot of people saying, well, this one's like slightly better than this. At least we didn't see that like during the studies that we had. So I think sort of people get a sense that like these are, relatively close to each other, so that's okay. The problems are like the bigger differences and how to fix those.
She's pulled them over, or it is the week before bid week, and nobody happens.
Yeah.
So it seems to me like the target user for this at the moment are people who are already machine learning experts, already doing this sort of work. Do you see any sort of opportunities to bring in people like novices or people who are not machine learning experts in like applications for that?
Yeah, for model tracker or in general? Yeah. Well, so with the model tracker, the studies we did, we had a range of users. So not all of them were machine learning experts. ICE is actually designed for non-experts. So we have some people who are somewhat familiar with machine learning, but not wouldn't consider themselves as experts. And I think that is something we really want. And something like model tracker, I think, is actually useful for novices because you can learn by seeing the effects of your actions over time, right? You can see that features make bigger differences than labels, and that's something that maybe machine learning experts are already familiar with, but novices maybe are not. But it also just happens that like machine learning experts want this, like to use this tool too, right? Because it was just hard for them to access their data beforehand. So I think it benefits both. And I think there's a whole spectrum of dealing with end users even, so people who are not even trying to build models, but just trying to use machine learned models in their day-to-day lives when they're making content recommendations. Right now there's not a lot of tools for people to steer those recommenders to sort of suggest things that they're interested in, except for liking and disliking things, to experts who are trying to build new algorithms in this. So there's a spectrum, and I think some of these tools can translate and work well across the board, and some you need to design specifically to the application and task at hand. Yeah.
I have a few questions.
Yeah.
The first one is, I think this is great. The model tracker is great. I'm a little confused about, so it's really great when you think about changing mislabeled data, right? But every time you change your data, you would probably have to tune your hyperparameters again. So does this application take that into account at all when it retrains every time you change your data? Because presumably you'll get completely different allocations of assignments, classes.
Yeah, so in ICE, we do all of that sort of behind the scenes. We tune parameters behind the scenes. We don't expose that to the user. So yes, that does impact things, and we currently don't sort of expose that in any way so that people can regularize more or not, or change the algorithms. In fact, what the initial idea with ICE was to sort of to hide all that from the user, and even change the algorithms, not even the parameters, but change the algorithms altogether as you go along to figure out which algorithms are best suited for the labels that you have. I think there's pros and cons to that. If you're an expert, you want to have more control. If you're a non-expert, what do the parameters mean? How do you even know what to do? So I think it sort of depends, again, sort of like how much control you want to have. And if you do want to have more control, then yes, I think you need to expose them in some way. And we don't really know how to do that effectively.
And the second question I had was, right now you're showing, you said about 200 pages, is that right? Or
500 pages. Yeah.
Right, and that's something that you can easily visualize, right?
Yeah.
Using what you have right now.
Yeah.
But as you grow your data set larger and larger, presumably if you have 1 million different data points, how do you take those into account?
Yeah. So with ICE is designed for people to sort of build models in a few hours. So they typically get up to like 500 or 1,000 examples. We also use model tracker for entity extraction, which often it's at the token level, so we can have about 10 times more examples. And for that, we subsample. We subsample and show you just a subsample of that in model tracker. We're also looking at different ways of sort of grouping data together. So you can see sort of groups of, instead of individual examples, you can see groups at the different positions, and then use that to sort of dive in more. So yes, the larger data sets, we have, there's more things you need to do for that. Yeah.
Is there any significance in terms of how the different data points are laid out vertically, or kind of?
Oh yeah. Yes. So okay, I didn't talk about this, but the bottom half is showing you the training data. The top half in ICE is showing you the test data. And that's because in ICE, we automatically split the data that the user is labeling because they're starting from scratch. So we need some set that's for use for testing. Now we've talked about this because so looking at your test data is not, I mean, you have to sort of do it at your own risk, right? Because you can overfit your data if you look at it too much. But because mislabels happen in ICE, we expose people to the test data. Now we're looking at sort of getting rid of the test data, so the stuff at the top, just considering all of it as training data and doing cross-validation, so we sort of eliminate some of those issues. Other than that, we do so often if you do have a lot of data, as your data set grows, these can sort of go off the page, and so we sort the problems to the middle. So there's a line here that sort of splits the top half and the bottom half. So we sort all the issues to the middle, so that even if your data grows and it goes off the screen, you know that all the stuff off the screen is correct, and so you can still have access to your errors. Yep.
Well, so you mentioned the issue of overfitting. Mm-hmm. So did you ever see the case where people were responding to these errors by then creating more and more features? Is that an issue that you might see occurring because people have such direct access to this?
Yeah, so this is a really interesting question. So, and this kind of goes back to Michael's point, right? So people want to click on their errors. They want to click on these things. And it might mean that they might start over-engineering their models, which is not necessarily good, right? So we don't really know what the impact of this is on whether or not they're overfitting. We like the ability to have it always available so you can interact with it. But if it is distracting people, then we might want to sort of have people sort of pull it up periodically or that kind of thing.
Well, I wonder about maybe visualizing degrees of freedom and how that's changing too.
Yeah. How complex your model is becoming.
That interplay might be cool to visualize.
Yeah, and I think some of this can be learned actually also over time, and if you can sort of go back and forth, between sort of removing features and seeing if your performance goes up, or sort of maybe we can keep track of good states and bad states and sort of help people sort of compare that. Well, you were at a better state when you had fewer features, and sort of show the comparison in the visualization or something. But yeah, it's definitely, people do want to interact with it, and that's what we wanted, but maybe it's too much. We don't really know. Yeah.
I might have missed this. You mentioned that you were using this for multi-class classification as well. How would you use that for that?
Yeah, so we convert multi-class to binary. So for each class, you can view the performance for that class versus everything else. So you have to switch between it. And again, I don't think that's optimal. I think there are better ways that we can try to design new visualizations that show all of the classes at once, and that's something we're interested in. But right now, we use it in that way. And I mean, people still use it. People still find it useful. But I think there's more we can do.
The same way that you collected labels. So in the first project, you worked on how do people actually collect labels and helping people do that. So for the entity extraction, is that something you guys have thought about, how to facilitate that, or have you looked at work in that area? Or?
Yeah, well, so I mean, people collect labels with entity extraction as well, right? So they'll
what they're doing in the model tracker version is also doing all the labeling.
Yeah. With ICE, you do start from scratch every time. So you'll explore the universe. If you're creating an address extractor, for example, you'd find some addresses, label the tokens as this is the street name, this is the city name, that kind of thing. And each of those tokens then turn into a box in model tracker, and we use a CRF for the entity extraction model behind the scenes.
This perhaps just a suggestion visualization wise. So once you get rid of the training data from the visualization, essentially your y-axis becomes free, right?
Yeah.
I think you could potentially visualize features like that. Just you click on a feature and then it shows vertically. This is the positive, this is the negative. That way, that shows what the impact of the feature on the final classification is.
So you would spread it according to a feature. You mean with an animation
feature
kind of thing?
Top is the positive, negative examples, right?
I see. So we show feature correlations with like overlaying, highlighting for some of that. But yeah, I mean, I think yeah, if you, right, the y-axis, so it's not showing you much, but it's showing you the distribution, which can actually also be informative. So I think there's opportunities to change between like spreading it in one way and then going back to the distribution. And yeah, we haven't sort of explored the other axes and how we can sort of lay it out using other information. But yeah, I think that's a good idea.
Okay, let's thank Saleema one last time.